train station at Hirscheid. So the train is not running actually, so nice to see you all here. So the idea, last week we stopped by query execution methods. So the different kind of executing query operator plans, so Volcano, which is with the next operators, and also with produce and consume, and I think vectorized processing and blockwise processing. So that was what we learned last week. So the different kinds of query execution, and now the idea is how to make it fast. So the idea is today we first will look into parallel query execution, so that you add operators to parallelize the engine, and then we will have a look at modern database systems. So main memory database systems, how they optimize the storage layout, and what kind of index structures they use beyond B-trees. So that's the agenda for today. So let's first start with parallelism. And so the idea is, okay, why do we need parallelism? Of course, like the first thing is we have multiple users at the same time. So we want to have multiple queries running at the same time. But also what's the idea is that we have two kinds of parallelism. The first one is interquery parallelism, and this is actually the same with multiple users. So we have multiple users and sending queries to the database systems, and we want to answer them in parallel. But for that reason you have multi-version concurrency control. And the second thing we have is intra-query parallelism. The idea is, okay, we have a single query, and how can we make this single query fast? And that's actually what we are focusing on. So the idea is, okay, two possibilities. So horizontal parallelism, that we execute the subplans individually. So first we do the table scans, and afterwards we can perform the projections and selections and so on. But I think the most common one is vertical parallelism. So that we say, okay, we have our database system with multiple tuples, and we can say, okay, the multiple tuples are executed in parallel. And that's the vertical parallelism. So, I said we have to introduce more operators. And basically, and that's also the idea, if you have heterogeneous hardware, the idea is, okay, you have here an exchange operator. So now we can guess what kind of operators this should be. Actually, I don't know it, so I think one would be, for example, a selection, another one would be a projection, and here in between, of course, this is an aggregation. So the idea is, okay, this is an aggregation, so this is in gamma actually. Sorry for the bad symbol, so this is the aggregation. And the idea is, okay, so we have here a single query plan having somehow an operator, for example a selection here, and then actually what we do is aggregation afterwards. So aggregation, what kind of operator is it in SQL? Just to recap. Aggregation, what is it? How do you make an aggregation in SQL? What's the clause? What's the keyword? Group by, exactly. So this means that this is a simple operation, simple SQL query with a group by at the end. So we have kind of a group by at the end. So this means we have an aggregation, and the idea is, okay, so if we have multiples, for example, if we have multiple keys, and if we perform for each key, we first execute it in parallel. For example, we have one relation, 1, 2, 3, and with some keys, okay, we need at least one more. Then we have one relation with more, for example, with a lot of 2s and a lot of 3s. So what we do is, for example, if we do the count, so if we have a count here, so we would have, okay, 1, we counted for the first aggregation 2 times, 2 we counted 1 time for the first partition, and so on. And then we do the same for the second partition, and then afterwards for the third partition. And then, so this would be done here, and then we have a final aggregation to unify all the different partitions. And that's the idea, okay? I've introduced vertical parallelism by using this kind of exchange operator. that's it actually. So currently, Michael Engel and I, we submitted a proposal where the idea is, okay, we have different kind of hardware, for example, a GPU here, for example, near memory processing device, so an SSD with compute capabilities, and then a normal CPU, and we want to do we store the data at different hardware, and then we want to compute the aggregations on each hardware before we do a whole aggregation at the end. So basically that's it. Just introduce exchange operators for intra-query parallelism. Okay, so what kinds do we have? So here, this is the first one. We have n input pipelines and m output pipelines. Then what we can also do, instead of, if we want to unify it, we have this kind of union operator. And in the other direction, if we have one input pipeline, we have the 1 to m. And then we can also do a hash. For example, if you know the different kind of partitions, for example, all the keys with number 1, 2, and 3 should be part of a different partition. We have this kind of hash. And then we can broadcast every partition to all the consumer, and then we can also make ranges instead of hashes. So these are the kind of exchange operators we can add to the normal query plan to achieve intra-query parallelism. So here we can see another operator. So here's the aggregation, and then we can see, okay, if we have the hash split, so normally if you compare it to the first one, because you don't know the different, so this is a random partitioning. So you don't know which kind of keys are in each relation. So every key can be part of relation 1, 2, and 3. So you have to perform another aggregation at the end. Instead, if you say you have a hash split, so you first already split the data into multiple by the key, so you don't need any aggregation at the end. Yeah, and basically that's it. So I really wonder about the symbols here, because like the symbols seem totally broken. I'm sorry for that. Because actually this shouldn't be a B, this should be a join symbol here. Because like it's a join with the exchange operator. And here the idea is, okay, if I first hash, I split the keys, I split the partition by the keys, I can say, okay, for example here, I only have, I do a join over the ones, for example, if I have the key ones, and here I do a join over the keys 2, and so like this I can hash join, but a distributed hash join kind of. So actually it's not distributed, but a parallel hash join. So this is an example having the hash operations, how I can achieve a fast join operation by hashing by the keys itself. So if I have here my relation, and my relation consists of a key, for example 1, 2, and 3, so then I can say, okay, the ones should be here, the threes, the twos should be here, and the threes should be here. So that's the idea of hash split. Already pre-partitioning, and then I can do the same for the table on the left side, because like here I have another relation. We have also the join key here, 1, 2, 3, and so on, and another value, so value 2 and value 3, and at the end I want to get my relation with value 1 and value 2. 1, 2, 3, 3, and so on. So this would be the idea. So that I use hashing already for the input data. So also here I hash the data before I compute it in parallel. So that's actually the whole idea of having an exchange operator. So this is traditional parallelism if I would have kind of an volcano model. So the classical query execution approach. Okay, what are the disadvantages? So static work partitioning can cause load imbalance, so you do not know what kinds of keys occur more frequently than others. So you do not know about load imbalances. Degree of parallelism cannot easily be changed mid-query, because like, okay, you have your 3 partitions and you say this in advance, so you cannot be adaptively, you cannot you cannot change the degree of parallelism adaptively to the workload, and you have some overheads because like you need more threads than CPU cores, okay, and hash repartitioning often does not pay off. So sometimes you have more overhead by introducing more operators, and also if you have operators for exchanging the data, this sometimes means to materialize the data beforehand, and thus you have more overhead. Especially if you are dealing with different hardware, you have to materialize the data, so you have to stop a pipeline, and this is bad for the performance. Okay, so then the next idea is, okay, how can I parallelize the operators instead? So instead of adding some exchange operators, the idea is, okay, I parallelize each single operator. And therefore I need some shared data structures, for example hash tables that allow for parallel inserts and parallel accesses. And yeah, and this is more flexible. And the idea is, okay, I will introduce now a concept my PhD advisor introduced, and this is called morsel-driven parallelism. And basically it's just work stealing. So if someone knows work stealing, like you have GPU worker threads, and each GPU worker thread asks for another tuple. So that's actually how it works. So currently I have one student who's actually two students who are currently working on morsel-driven query execution on GPUs. So the idea is, how can I optimize the load on GPUs by morsel-driven parallelism? And the idea is, okay, so two things. So the first thing are the morsels. And you see I have, for example, here, you see three tuples, and those three tuples form together one morsel. So this is one morsel. And basically the idea is, okay, that's the granularity for work stealing. Like we have multiple threads, and every thread is asking for one morsel. And actually that's it. Actually, you have just one thread, and each thread asks, okay, so we have like this partitioning, and every thread we have one global counter. And for example, this is the first morsel, this is the second morsel, this is the third, and this is the fourth. And then we have one big counter, and every thread says, okay, atomic counter, give me the next one, and these are the morsels I'm working on. And here, this is the example for a hash table. So now we can guess what we are doing here. So, okay, so it's a basic join. So the idea is, okay, we have two relations, T and S, and one side should already be materialized. And then, okay, so like we have a query plan, and we have a join. And the idea is, okay, we have a pipeline, and R is part of the pipeline. So here, the pipeline, one side is R and the other side is S. And the idea is, okay, let's use another color. So the idea, okay, everything which is part of the first pipeline is part of the hash table. So this has already been hashed. Okay. Okay, it's more complicated because like we have two joins. The idea is we have two joins here. And we have another join with T. And the idea is, okay, this is the other pipeline. So the idea is, okay, we first materialize S and we materialize T. And then we can get all the tuples from R. And basically what we do is, okay, we check for each tuple first whether there's a join partner here. So like we see the S relation, so the S relation, it's just here. So the S relation has two attributes, A and B. And basically what do we have? A is 5, 7, 5, 7, 16, and so on. and the other value is the other, as we can see here. 5, 23, and 8, and so on. And the same for t. And basically what we do, we build a hash table, and as you remember, hash join are the fastest for equality. So what we basically do is, okay, we first check, here the join is the attribute a of, so r.a, is it equal to s.a? And here for 16 we find a join partner. So check, join partner found. For 7 we find a join partner. For 10 we don't have a join partner. Then we, again for 27 we have a join partner. For 18 we have a join partner. For 5 we have a join partner. So 7 and so on. So this is the first thing, and then we compared to what? Then we compared again to b, and then we can see, okay, for 8 we do have a join partner. For 33 we have a join partner. For 10, for 5, 23, and so on. And then we have the final result. And the final result basically is just joining all the attributes together. And why is it in red and blue? Because like we have two threads. So here we have two worker threads, and basically the idea is we have a blue and a red one. So currently only if we would have two threads, and the idea is, okay, granularity 3, so the first worker thread consumes the red tuples and the second one the blue, and as soon as the red one has finished, it goes on to the next, and so on. And finally the result, so everyone receives a different location where it stores all the results, and finally we put these results together. And that's the idea. So like you have this big pipeline here, and remember we have pipelining, so we first materialize one side for each join, and then as soon as we have materialized all the left sides, we can continue from the right side. And we can run for each query, we just compare it with that, and then with that, and then we can store the result here. And the idea is, okay, every thread knows what to do, and every thread asks for the next tuple to process, and the granularity is called morsel, and here the granularity, for example, is 3 tuples together form a morsel. And this is like, I think it's in the configuration of the database system. So when you write an operator inside of the database system, you have to decide on the morsel side, on the morsel size. Yeah. So actually it's just work stealing. So morsel driven is just a nice keyword for advertisement, but actually how we would call it instead would be work stealing. So morsel driven is the same as work stealing, but for database systems. Because like the granularity on which you work on is a multiple of a tuple, and this multiple of a tuple is called morsel. Easy, isn't it? By the way, if you want to know more about it, you can work it as a master's thesis. So currently I have one student working on it, and currently we try to benchmark morsel-driven query execution for GPU database systems. That's what we currently do. Okay. Actually, it's a nice picture. I like it. Okay, dynamic scheduling. So what it is, what do we know here? Total runtime of a query is the runtime of the slowest one. Okay, that's for sure. When dozens of cores are used, often a single straggler is much slower than the others. And therefore, solutions don't partition input data at the beginning, but use dynamic work stealing. So as I said, like it's work stealing. And synchronized queue of small jobs, and the queue of jobs is just one morsel, and threads grab work from queue. Okay, so far, so much I already explained, and now the question is how can you do it? And actually there's parallel 4. Who already has tried it out, parallel 4? No one? Really? So actually there are two possibilities. So So there are two possibilities for a parallel 4. So the first one is Intel TBB parallel 4. Let's have a look. And it's quite easy. You just use it like a normal for loop. And where is it? Okay, I don't like the... So actually it's like instead of writing a for loop, you write parallel for. And now we have to find any parallel for loop, but we don't. Where do I have examples? I have examples on my laptop, I'm for sure. But where are they? I think I had... if I remember correctly, it's called ML2SQL. Yes. And now what we don't want to... So either it's a parallel 4, but I'm not sure whether we have implemented, but then we have to find OpenMP. Okay, so I think it's matrix operations, and I think it's in source it is, and now let's find open. No. Okay, I'm not well prepared for that. OpenMP. Open. So like there are two possibilities. The one is parallel 4, and you have like from Intel they are called threading building blocks, and you can just use it as a normal for loop, and you have to define the granularity. So you have ranges. You have to, I think in C++ there are ranges, and you say okay, begin and end. So you have your big for loop, and you partition it into smaller ranges, and then within each parallel thread you're working on a certain range. So this is the one possibility, and this is actually called parallel 4 from Intel threading building blocks. And there's another one, and it's OpenMP parallel 4. So and like this is more easy because you can just reuse your current for loop, and you just have to add it with pragma or MP parallel 4, and then everything what is inside is actually parallelized. So these are the two possibilities to parallelize easily with C++ without using threads. So you can have a single thread, and from the single thread you can parallelize easily. So this is actually the easiest way to parallelize a for loop without using C++ threads. Yeah. I'm still wondering why I don't have it. So OMP parallel 4. Actually it should be here. OMP, okay. So which file is it? Yeah. And so what we did here, so we wanted to make array operations to work as matrices, and basically what we did, we added operations, and what kind of operation is that? Matrix multiplication, for example, and we parallelized each entry here using a parallel 4, for example. So here, this is actually each entry of a matrix, and we parallelize the computation using OMP parallel 4. So it's quite easy to use. And I'm for sure I have some kind of examples for using Intel threading building blocks. I can show you later, maybe before the break. Okay, so the idea is, okay, use parallel 4 for parallelization. Okay, so then I have here an example for a parallel in-memory hash join. And how can we do it? So like if you remember, the first side is the build side. So as always, if we have a join, remember we have a build side and we have a probe side. And the idea is, okay, the build side is the first pipeline, and then the probe side is part of the other pipeline afterwards. So it's always like join side. Join is a pipeline breaker on the left, so on one side. So it's not a full pipeline breaker because the other side can continuously produce tuples, but the other side is being break the pipeline. Okay, so the build phase, so that's the red one, that's the build phase. And yeah, each thread scans part of the input, it materializes the input, create table of pointers of appropriate size, scan materialized input, and add pointers from array to materialized tuples using atomic instructions. Okay, you have to just do it on the left side. And probe phase, it's easy to do it in parallel because like you have the hash values, like you have a big hash table with key and values, and as it is read only anymore, so this one is read only, so you can do it easily in parallel without synchronization. So you only have to take care when building the site, and therefore you have like an appropriate size, like it should be bigger than the sum of all threads. So every thread should work on its own range, and at the end you can summarize it. Yeah. Because if you have the same key in separate ranges, you have to consolidate. Okay. So this is how you can parallelize on traditional query engines. Okay, questions? If it's not the case, so we can continue to main memory engines. And now you will learn everything about main memory databases, so examples like SAP HANA. So this is one of the most common main memory databases. And what was the history? So basically the history was SAP, or better the institute which is associated to SAP. It's the Hasso-Plattner Institute. So if one has enough money, so you can found your own institution and make yourself a professor like Hasso-Plattner did. And like he said, okay, he initiated some workshops and he said, okay, we have these trends, like the main memory capacities. And yeah, maybe I show you my latest proposal I wrote with Michael Engel. And so if you ever want to know how your tax money will be used for doing some research, so the idea is, okay, you have this figure, and here in this figure you can see like, so it's a traditional figure, you have the costs of US dollar per megabyte, and you see basically it all decreases, but you can see that all the others, I can't see my mouse, okay, so when was it? So nowadays SSDs is decreasing faster than main memory, so this is main memory and this is traditional hard disk. But what you can see is also that actually SSDs become as cheap as HDDs, so like hard disks, so there's no need to buy a hard disk anymore. And there was a time when actually RAM was decreasing more than SSDs. So here, like this was the time when RAM was the cheapest. So then the money increased again. So actually this was the time when main memory database systems have been established. So we saw that actually RAM was decreasing, the price for RAM was decreasing more than it did for SSDs. And then we said, okay, let's put everything into RAM and do not consider the HDD anymore. Nowadays you see SSDs, the money for SSDs are decreasing, so currently the trend shifts towards using SSDs again, but no one uses HDDs anymore. And we are not talking about this point in 2016 when we said, okay, RAM is more achievable than SSDs. Okay. And then you see the hardware trends. Huge main memory capacity, have many core CPUs, and SIMD is called single instruction multiple data. So who has heard about it, SIMD? So normally if you have like in computer architecture, like you have two registers, and the idea is, okay, a register is as large as you have as your computer architecture. So initially it was, I think, about 8-bit. Then we had again 16-bit. Then we had 32. And now we always use 64-bit architectures. And I think, how is it? I think until 32, it's EAX called the register. Okay, and now the idea is, okay, we have a separate SIMD unit, and the idea is, okay, instead of 64-bit, 220. Now 64, not 220. And like the idea is, okay, instead of 64-bit, like we can use up to 512-bit. So we have 512-bit, and then we say, okay, inside of 512-bit, we can process up to 8 64-bit numbers at the same time. And that's the idea. Okay, SIMD means the same instruction on multiple data. So that's the idea of SIMD, and therefore I can easily parallelize, like if I have up to 8 data values, and if I want to do the same instruction like we frequently do in database systems, we can just parallelize it. So we have, okay, new CPU features. So HTM is actually hardware transactional memory. So the idea is, okay, if you remember the first lesson we had with transactions, and like you have the atomicity of a transaction. And the idea is, okay, is it possible to achieve this also on the CPU? So we do not need a database system anymore, but we can say, okay, we have instructions for do it all at the CPU. And they were introduced, and I think it's about up to 8 instructions, and they are and they ensure atomicity for up to 8 CPU instructions. So some CPU actually support it. So do you smell something? Is there, I think, I hope only if there's making some barbecue outside, so we close the window. Can you please close the window over there? I hope so. Okay, and some other features we have, like GPU, and that's currently what I'm doing. So like if you remember, like GPUs basically excel in having the same as computing the same instructions on multiple data, because like you have multiple pixels, and basically you have to do the same computation on all the pixels. So basically graphic cards, so graphical processing units, GPUs, and what they do is actually SIMD processing. But SIMD, it's called on CPUs, and on GPUs it's called threads for whatever reasons. So actually what a thread in a GPU does is actually what the same as we do in a SIMD processing on CPU, but like with a higher granularity. So it's called general purpose GPU programming. So you can also use the graphic cards, and graphic cards excel in SIMD processing. So there's also another, so it's also called data level parallelism. That's the official name, data level parallelism. So data level parallelism. And SIMD, it's on CPUs, and data level parallelism on GPUs, it's threads. And for those who are interested, like 32 threads, this is the unit with you count on GPUs, like you always have, like on CPUs, you have like registers of 512. And normally, if you have 64-bit integers, you can process 8 integers at the same time. And on GPUs, you always have a bundle of 32. And 32 threads together is called a warp. And you always have to calculate in multiple of warps. Like this is GPU processing. And FPGAs, they are programmable. And Michael Engel is a bit sad that we do not have anyone focusing only on hardware. So the idea is, okay, you can create your customized FPGA to do whatever it should. And like we have also increased network, for example, InfiniBand, so it allows you remote direct access memory access, so you can bypass the CPU, you can directly access the memory of another machine. So this is called remote direct memory access, RDMA, and this is with up to 1 gigabyte. I think it's gigabit per second. So I have it on my proposal. If we have a look on it, where's my proposal? I have all the numbers attached somewhere. So 10 gigabyte per second it is. So basically that would be a modern architecture. Like you have the DRAM and you can access the DRAM of the other node directly using InfiniBand. You can access another GPU using NVLink, and also all the other kind of compute storage you can access directly. And you also have the normal InfiniBand connection, so you can Ethernet connection. So you can access the main memory directly. You have the normal connection via Ethernet, which goes over the PCIe bus, and then on the PCIe bus, the GPU is connected, and the GPU, for example, has streaming multiprocessors, and the streaming multiprocessors, yeah, and they actually, this is the unit which computes in multiple of warps. Yeah, so this is kind of a modern architecture you have. Okay. And now the idea is, okay, let's make use of it. And the idea is, okay, the first idea, so we were in 2016, the idea is, okay, the entire database system fits into main memory, and new types of database systems should be developed for that, and new algorithms, new data structures. So, recap, what is a database workload? So, like we have two kinds. What are the two kinds of database workloads? So analytics and transaction processing. So what's the common term for that? Analytics, so what's the abbreviation with O? Yes? Loud?
Sure.
I'm not sure.
I was thinking I.O.
No. So it's, yeah? Yeah, it's online analytical processing, OLAP, and OLTP, online transactional processing. And the idea is, okay, before that, like we had two database systems. Like all the data warehouses, they had one for the transaction. So if you buy something, you had the transaction processing, like with all the customers buying another item, and they are short running. They have simple queries, so just add something to the data. It's mostly insert, update, delete. And this is OLTP. And the other idea is, okay, normally each night, like all the data warehouses, they were running one big extraction process, transferring all the data which have been created to another database server just to do all the analytics. And the analytics were about long running, aggregating all the customers' data, aggregating all the buys, what has been bought, and therefore they should have access to large parts. They scan a lot and they are read-only. And the idea was, okay, how can we combine that? So, and that was basically the big question, how can we combine it? And this was then called HTAP, so hybrid transactional processing. H. Oh, this should be an A, H tab. Yeah. So here again, OLTP, like the transactions, and the idea was, okay, in the 1970s, database systems were optimized for transactions, like getting new input data, and so we only have a small fraction of the database in the memory buffer, so we had all the data swapped out to hard disk, and therefore we had a lot of disk accesses, and we did not care about the costs. And nowadays, okay, we store the whole data in my memory, and we say, okay, it's enough what fits into memory, all the other things can be compactified and swapped out. And okay, transactions is one shot, so not long running, and they execute in a few microseconds or milliseconds. And therefore, what are the overheads? As you remember, the Aries style logging. So Aries was the recovery protocol we learned. So then, of course, we have the locking. If we want to have write access, we have to lock it. Ledge is kind of another lock, and the buffer management when swapping out pages to disk. And now the idea is, okay, how can we avoid this overhead? Okay, so the first thing we did, like we changed the memory layout. So the idea is normally you have like a row store, and row store means okay, row store is every line by line. So of the first line, the second line, and they are stored consecutively in main memory. So here you see it, we have the first line and so on. And then we have the second and so on until we reach the fourth one. So this is actually how OLTP database systems store data. For example, if you have SQLite is a row store, and in contrast to it, DuckDB, it's column store. DuckDB is like SQLite, but optimized for OLAP, for analytical data. Now the first thing is that, okay, instead of storing it like that, as a row store, the first thing is, okay, let's do a column store. So here we have first the keys here, then we have the prenames, then we have the surnames, and finally we have the salary. I think salary is written with A, isn't it? Okay, so that's the first idea. Okay, we use column store. And column store make it easy to aggregate data. For example, if we just want to sum up the salary, we are not interested in the other two columns anymore, and therefore we can have the salary, and basically we can cache the next data. Like you remember the hierarchy, the memory hierarchy you have, and like we have the registers at the top. We have like L1 to last level cache, so L3 cache. Then we have main memory, MM, and then actually we have the hard disk or the solid state disk. And basically in last level cache, so cache line is 64 kilobyte, and therefore if we only have one column, we can cache more data of one column which we are interested in, and therefore we make analytical queries, for example, aggregations faster. So this is actually the reason for column store. We can all cache the whole data of one column. So and therefore we are faster for analytical workloads. So column store faster in an analytical workload. So here again the summary. Row store, it's good for OLTP if you change the whole tuple, because like you cache the whole tuple, modify it and write it back, and therefore row store is good for transactional workloads, whereas column store is good for OLAP, for analytical workloads. And what's also good is you can vectorize it, as you have the same, if you have a single value, you can use SIMD instruction for vectorized processing. And if it's like the same kind of data, you can compress it easily. For example, you can do some offset compression. If it's all the values, for example, start with 1000, you can do some prefix compression or something else. And for sure, they have an excellent cache utilization. And here is an overview about the systems they implemented. So Microsoft, for example, is for Microsoft SQL, the database of Microsoft, they have introduced an extension, it's called Hackathon. There was, I think it's also from MIT, which is called VaultDB at HStore. And like you have OLAP only, like vector-wise, MonetDB and DB2BLU, and like the HTAB database is like the most common one, and the commercial one is SAP HANA. Then there's Hyper, which is actually sold to Salesforce nowadays. And yeah, the successor from TU Munich was Umbra. And there's also like the file-based one, it's actually called DuckDB. And yeah, and also there's another one implemented by a colleague, it's called LingoDB. And actually most of the companies, they're developing a system on their own. Like if you go to Amazon, Amazon is developing a main memory database system. Firebolt, Snowflake, and all the big tech companies, they are developing database systems on their own. So if you're good at programming database systems, it's also good for your salary. Like there are only few who are good at programming in C++ for database systems, and database systems companies are always looking for developers in C++. Okay, so the challenges, we still want to guarantee ACID. So that's also the difference to NoSQL database systems. Like NoSQL is just a key value store, and they do not guarantee you the ACID properties. And as soon as your data is valuable, you should guarantee the ACID properties, and therefore and of course, if we create a database system, we have also to guarantee the ACID properties. And how do we do that? So for in-memory database systems, we do not have a buffer management. So we say, okay, we do not force it out. So we cannot steal data, but if we have a loss of, if our database system crashes, we have to recover, we have to redo all the logging steps. Oh, I'm running out of battery. So that's the downside. So if you have running an SAP HANA system and you're losing power, if you have a power loss, you have to redo all the entries. So you have always to create some redundancy and, for example, run two database systems in parallel. Okay, so logging, you have to ensure logging, of course, for recovery. So you have to do to record it to another node. And locking is also important. There are some database systems who only do serial execution of write workloads. And latching, okay. Okay, here's an example of Microsoft Hackathon. So it's integrated, as I said, in SQL SQL Server. And yeah, they have kind of another database index structure. It's called the BW tree. Some mean people say it's just called the buzzword tree. That's why it's called BW tree. And it's not very good performing, but actually here it's a B tree and a hash table on the same data. And okay, there are also some OLAP systems, and we will have a deeper look into Hyper. And basically, vector-wise is basically the predecessor of DuckDB. So vector-wise is from Amsterdam, from CWI Amsterdam, and they have also created DuckDB. So if you cannot read my writing, just imagine a duck. So, duck. Maybe it's better than my writing. Maybe it's my painting better than my writing. Okay. Now the idea is, okay, let's mix OLTP and OLAP to avoid any ETL, so in extraction transform load architecture. So traditionally you had two systems. One for the production, where you write all the data, like in a data warehouse, where you enter all the purchases, and one to analyze it on the next day, and in the night you have to extract the whole data. Okay, and then the idea was, okay, SAP HANA was the first one. Everything, so they optimize for reads, and basically what they do is they have one big delta store, and everything which has changed the data, or the changed data items, they are part of a big delta. And therefore, if you read data, you have always to ensure that you have an old state if you read it, and if you change it, you have to read both the delta and the main memory. And Hyper instead, they did a fork, so like they had virtual memory snapshots, so they forked the whole pages, and therefore they created new entries only on demand. So basically that's here the idea of forking. So the idea is, okay, you have like the OLTP transaction running, and as soon as you have an OLAP query, so if you remember, there's the fork command. So if on Unix, and on traditional Unix, if you want to create a new sub-process, you can just say fork. And then you are running two processes, and the first one, and I think, and you can check, so you have big if fork, and then you have to do a check on the process ID, and then basically you are working on a new memory layout. Basically what it is, it's a virtual memory, so basically this is everything a pointer to the old data location, and therefore you can see here's the pointer to the old memory location here, and as we update a data item here in main, then we copy it only on write, and then so this is not a pointer to the original memory location, but then it's copied, and that's actually the idea. We have virtual memory, and virtual memory just is a pointer to the old one, except data is written, and that's basically done using fork. So it's not how it is done nowadays, but this was the traditional approach, and the fun fact about it was like the fork command is, I think, from the 1970s. It's one of the most traditional thing how to create a new process in Unix, and they reused it for a database system, and they reused it to ensure ACID capabilities, so that you have, so to avoid cloning the whole data. Yeah. So for all the other pages, you still have access to, you have still a pointer to the other data. Okay. Now let's talk about in-memory index structures. And the idea is, traditionally you have a B tree. B tree is actually optimized for pages, so for hard disk and swapping out pages to disk. And now the question is, you want to create a key on a database system, so you have like a key on data, and you want to have fast access. And the question is, if you do not need a B tree anymore, how can you still ensure fast access? And yeah, there are three possibilities. The first one, in-memory hash indexes, simple and fast, but growing is very expensive, and they do not support range queries, like it's just a point lookup. The traditional idea was about B trees, but they are designed for disk. Now the idea is radix trees. Who has heard about radix trees so far? No? So radix trees, maybe let's first start with this slide. So like the idea is, okay, radix tree is just a prefix tree. Sorry? So radix tree is just a prefix tree. And this is also called a trie, for whatever reason. And the fun fact is, okay, like if you have for the complete alphabet, you have like 20, so if we say, okay, we store we store strings, and for example, we store strings of size 3. So we see the height of the radix tree is exactly the size of my key, so it's 3. And how big are the nodes? And each node is as big as the range is. So if we have like normal characters, like the range is 26. And then okay, we can just, so like we have split it up, like the first is here, the second, and the third here. So this is the third, and the second. And basically what we do, okay, we put in our key, for example April, and then we have a pointer here to P, to R, and we find our data. And this is actually a prefix tree. It's quite simple. So it's just, and for that we can use, for example, a hash table or any other kind. So to make it shorter than 26, we can just use a hash table. So if you implement it on your own, you would use a hash table. Yeah. And basically that's it. That's a radix tree. So, as I said, the height depends on the key length, not the number of entries. So you do not need to rebalance it, because like either the key is already part, or you have to create a new node. All insertion orders yield the same tree, so it does not depend on the insertion order like the B tree. And the keys are stored in the tree implicitly. So you do not have like kind of offsets or some, you have to look it up, you do not need a dictionary, you just know it by the position. Node is area of size 2 to the power of s, okay. S is a trade-off between lookup performance and memory consumption. Okay, so radix tree, I think everyone understood it right. And it's so easy and it's really nice to use it. And then there was one colleague, and he said, okay, how can we optimize a radix tree? And then he said, okay, we want to optimize it for cache locality, and he said, okay, let's have 4 kind of nodes. And he said, okay, like the regular trie node is the node 20, so the idea is, okay, we want to have it for keys. So the idea is, okay, we split up. If, for example, if you have 32-bit integers, and if you want to store memory addresses, then you say, okay, every level is 1 integer. So level 1, level 2, 3, and 4. So for example, for 32-bit, your height, the tree has the height of 4. So first, second, third, and 4. So if you have a 32-bit key, then you say, okay, you partition by bytes, so you have 4 bytes. So the idea is, okay, at each level corresponds to 1 byte. So that's the idea of the art. Each level, 1 byte. And therefore, if you remember our old slide, this one, if this is not a character but a byte, so this node would have a size of 256. Because like 2 to the power of 8. Yes. So the idea is, okay, every node, 1 node per byte. So, first idea. So, okay, if we have 1 node per byte, we have a node 256. So this is the regular trie node, as we have seen previously. This is the basic node. And then the colleague said, okay, let's tackle also some other kinds of nodes. And the first one is, okay, so if you have the node 256, maybe I show it on the next slide. Here you see it. And here it's implicitly. If you have the key, for example, 2, you just access this, the value at position 2. So it's just implicitly, the position is just the index you have. So for example, here, if you have the value 255, you access the last entry of the node 256. So you see, implicitly, the position is just the value of your key. So this is valid for the node 256. And it's also valid for the node 48, yeah, but with a small difference. Okay, so 2 nodes where the key where the key is implicitly the position. So it's here valid for node 48 and node 256. So the key is implicitly the position. It's implicitly the position. Okay. And then there are two other node types. And the two other node types, basically the idea is, okay, you store the key explicitly, and if you want to access the data, you have to compare the position. Like here, you have 4 positions. And basically you first look up for the key and which position is my key contained, and then you go by the key, and then you have a look up at the child point, and this actually points to the other node. So now the question: if we have a 32-bit if you have a 32-bit architecture, how big is the node? Node 4. How big is it? How big is one key? Or the part of the key we have? Every key is 1 byte. 1, 2, 3. So we have 4 bytes. And here we have pointers. So if we have a 32-bit architecture, each pointer is 4 byte big, and therefore we have each pointer has 4 bytes, and we have 4 pointers, so we have 16, we have 20 bytes. And that was basically the idea. If we have a node 256, we have we have 256 pointers. So how big is it? 256, 512, so it's basically 1 byte, so it's actually 1 kibibyte big. And therefore here you see the memory difference, 20 byte instead of 1 kibibyte. And that's the idea why you have different kind of nodes. And as soon as one node gets bigger, so if we enter the 5th key here, it will be transformed into a node 16, and then if we have more than 16 values, it will be transformed into a node 48, and if we have more than 48 values, it will be transformed into a node 256. And if you read the paper, there's also the justification why we need exactly these 4 node types. So like it was like some memory reasons, some time complexities he considered, but yeah, the idea is, okay, let's optimize a radix tree and have adaptive nodes. And yeah, and last but not least, we have the node 48, and the axis is basically like a child index. So here again, the key is implicitly the location, and then you have a pointer to the array behind. So here it's just less than 1 byte, and here you have to find the location, and then you can access here the pointer in the next node. Yeah, here's an example. So like you have here, it's the key as integer. So we first have to transform it into bit representation. So this is the first level. So of the second level, the third, and the fourth. And here you see, okay, we have the 13, so we access the 13. So we say, okay, it's in the first position, so here, it's here, and then this is a pointer basically to the next node. Then we see it's the 2, so implicitly we access the element which is at position 2. This is a pointer to the inner array, and here it's a pointer to the next node location. So we can go on. Where's the 9? 9, so we have a node 16. So we have to find the key. Here's the key. It's at position 2. So we have correspond to the position 2 here at the child pointers. And here basically the child pointer points to the last level, 255. It's a node 256. So implicitly the key is the position. And this basically points to our tuple in the database system. So this is the tuple identifier for any kind of data in the database system. Yeah. So basically that's kind of a nice index structure. A colleague of mine, he was afraid of teaching things that have been developed by a colleague. On the other hand, I've just reviewed a paper, and so currently there's a trend of substituting everything by a machine learning model. So in my opinion, it's completely nonsense if you have a working index structure and replace it by something learned. And yeah, so I was reviewing, actually I am still reviewing a paper how to substitute one node of that by a learned index structure. And so there are still papers dealing with the adaptive radix trees. So actually it became quite popular. But what I want you to know is how actually index lookup works. So I want you to know that it is a prefix tree, and if I give you a key, I want you to look up a position and whether an entry is contained or not. Okay. Questions? Yeah.
Is that page missing from the...
Yes.
Okay, then another one. In this picture it looks like it's going from node 4 to the node 256, but
No.
shouldn't it be the other way around?
I don't get your question. So
Like
it's about this arrow. So this one, right? Or what's the problem?
I thought because the byte representation starts at 13, it's just, because it goes from left to right, and I'm usually always think it's the other way around with byte, and also in the script it says the node 256 is the try node, which is in the search tree the first one. So
So it doesn't matter about the ordering. So
it doesn't matter.
so it's like it's just like it's by random that the first one is a node 4, the second one is a node 48, and so on. So this is by random. So it's always, you can also have like at every level a node 4. So if you only have, so you can have like 4 would be, so 4 times 4. So let me help with math. So if you have 4 to the power of 4, what is it? 4 times 4, so it's 16, 16 to the square, what is it?
So it's 254.
So let's do it. So 4 times 4 times 4 times 4. Huh? Like no one can see mine. So 4 times 4 times 4 times 4. So you can have up to 256 elements with only having node 4 nodes. So it's possible. So it's just, it depends on the range of each key on each node. So like this, the numbers here, they are by random. So it's just an example. So it could be also possible that you have at every level a node 4 node. You can also have like at every level a node 256 node, but then it would be the same like a normal prefix tree. And this is just an example to show you all the 4 kind of nodes. And it's just so, like, it depends on the number of keys you have inserted and the range of the keys. So if you like, for the first level you only have the range of 4 different prefixes, so then a node 4 is sufficient. If you have more than 4, then you need either node 16. If you have more than 16 kind of prefixes for this first level, you need a node 48. And if you have like 256 prefixes, you need a node 256. So this is by random. Is it now understandable? Other questions? Yeah, Gleis.
Are these slides also in the tutor set?
No, it isn't. Yeah, I should upload it. I did it in the train today. I thought it's not that important because, like, here everything is on the slide. And this is a nice example. Yeah, you can upload it. But you can also find it in the paper. So it's like the adaptive radic stream. ICDE 2014. Okay. So much about modern data structures. And yeah, so I never used hardware transactional memory. So originally, when I planned this lecture, I had in mind, so I'm giving two kind of lectures here in Bamberg. So the first one is basically systems programming in C++, where I learn all the things like using threads, and it will be on a Monday next semester. And I would be happy to see all of you again in my lecture, and it's about coding. So it's all about coding. So I was not sure, so actually last 2 years ago, I also gave this lecture, and I wanted everyone to also attend the other lecture, but I had no one attending. Oh yeah, two attending, but I was a bit sad about that, why no one wanted to do systems programming in C++. And so my original idea was, okay, I teach first systems programming in C++, and then I can teach you all the advanced stuff, like hardware transactional memory, like CUDA programming, like SIMD programming, and so on. So the idea originally was to teach you more about C++, but then I had only 3 participants in my original systems programming lecture, and I decided, okay, let's do some basics here and give you a big picture, a big overview about database systems in this lecture, and then motivate you all to attend my other lecture in the winter term about systems programming. So, and therefore, the idea, okay, such things, we do not learn it here, but it's a short introduction of hardware transactional memory. And the idea was, okay, let's have multiple instructions, up to 8 instructions, and let's do them as a transaction. So this should be executed atomically or aborted. And the idea was of Intel that Intel supports kind of ACID, like kind of transactions on their own. And like the main problem is they are limited in size and time. And here like you have the abort probability. So the larger the transaction gets, the more likely is it that it gets aborted. Yeah. So we see there's still the need for creating database systems to guarantee transactions. So the more data you process, the more likely it gets that the transaction will be aborted. Yeah. So for you, if you are eager to implement it, you can use hardware transactional memory. Yeah, and here are some examples of how to use them. So as fine-grained as two-phase locking, but faster. And here it's like this should be done atomically. So transfer the money from one account to another one. And this is how you could do it with hardware transactional memory. But as I said, I never used it. Okay, so what kind, and basically here's another idea. Okay, you have a big database transaction, and inside of your database transaction, you basically use hardware transactional memory. Yeah. So here, as you can see, you can use hardware transactional memory here as a building block inside of your database transaction. Just an example, but as I said, I never used it. Okay, so I'm not sure why we now explain NUMA architecture, but yeah, actually it's already getting old. Who has heard about NUMA so far? So basically, actually I think modern, so like the idea is if you bought a Xeon Intel server, the idea was, okay, the CPU cores, actually the CPU has grouped all the cores to sockets. And the idea is, okay, if you have 32 cores, they are grouped into 4 sockets, and every socket has access to its own DRAM. And the idea is, okay, all the sockets are connected to each other, and the idea is, okay, if you have a Xeon server which follows the NUMA architecture, you should be aware of that you can only process as much DRAM as you have per socket. And if you want to process more data, you need access to another socket, and this is expensive. Here you see the attached DRAM is 24, so has a bandwidth of 25 gigabyte per second, and if you need access to another socket, the connection is slower. And that's actually called NUMA architecture. It was like Intel built the systems like it is, and you should be aware of that. That's all. So it's not something good, NUMA architecture, it's just an architecture style. And the idea was, okay, Intel tried it out, how to maximize performance, and this was the style Intel created its Xeon architectures. But I think it's already deprecated. I think this isn't the case for Xeon processors if you buy a new one. But this was kind of the old one. And the idea is, okay, but if you have a server that follows the NUMA architecture, you should be aware of that. And therefore the idea is, okay, you have again your morsels, and therefore you should be aware that you can only process as many morsels as fit onto one NUMA node, onto one NUMA socket. So you can first partition it on one NUMA socket. So the idea is, okay, red should be done on one NUMA socket, green on another one, and blue on the other one. And at the end, you can consolidate to a global hash table. So the idea is, actually, you should have one for the red one for the blue one, and one for the green one. So basically, that's the takeaway of the 2 slides here. So 3 kind of threads, 3 kind of NUMA sockets. That's it. You should have heard about NUMA when I ask you, but we do not want to focus more on NUMA-aware data processing. But you should have heard the term NUMA once. Yeah. So if you remember the proposal, Michael Engel and I wrote. So actually, I want money from the German Association from German Research Association, and I said, okay, I first want to exploit modern hardware. So here, like, I want to exploit the different connections, and I want to exploit modern hardware like GPUs. And there was a second thing I want. So actually, this was Michael Engel's part. So here, by the way, here you see like exchange the data to another device, for example, to the GPU, and then process the aggregation locally, and then we have to exchange it back. So it's like the exchange operator applied to different hardware. And there's also one database system, it's called Proteus. It's from EPFL Lausanne, who has introduced the memory move operations for different hardware. Yeah, so this was my part of the DFG proposal, and Michael Engel had another idea. And his idea was, okay, let's use compression. And the idea is, okay, so normal InfiniBand, for example, has up to 5 gigabyte per second, and if we compress the data by a factor of 2, we can have a higher bandwidth. And the idea is, okay, like we have the different performance bottlenecks, and the idea is, okay, if we, for example, process the things that we are computing on GPU, for example, then we can have like a higher bandwidth to transfer the data to the GPU and process the rest on the CPU. So the idea is, okay, we want to compress the data. So this was the other idea. And yeah, so let's talk about compression. So where's my mouse? You see my mouse? I don't see it anymore, and here it is. Okay, so the idea is, okay, let's compactify the data. But how can we? Oh, you can't can't see it. So how can we apply compaction to data? So we have the same data model, we have fast modification, and now the idea is, okay, we want to use more memory, and how can we do that? And the idea was, okay, we can cluster the data. Like the idea is, okay, like we have the red parts are the ones that are accessed frequently, and the other things we do not access, we can compress them. And so the idea was, okay, and maybe we can also, if we have a beyond main memory database system, which also considers SSD, we can also swap it out to disk. And the idea is, okay, we apply different kind of compressions, for example, dictionary encoding. So instead of, if we have the same string multiple times, we can use integers. We can have run length encoding if we share the same prefixes, or we can also have kind of other compressions. Yeah, and therefore we can have a mix of regular and huge pages, so we can say the compressed data, we can put it on a huge page, and the hot data, so the red one, we can store it on small pages. And this was the idea of the data blocks. Like we have those which should be part of the main memory, and then they are cooling down, and afterwards we can compress them or swap them out. And this was kind of the idea how we can optimize storage. And how to detect that, for example, with software last recently used list, so we just we count the number of accesses, and there are also some kind of hardware if we have some flags, dirty and young flags, on our page table. Yeah. So it was introduced by my colleague Harald Lang, the data blocks, and the idea is, okay, we want to classify data into cold and hot. Yeah. And here are some other kind of idea. Okay, if we scan cold table, we have to decompress it, and the hot data we do not need to compress it. By the way, so I hope my proposal gets accepted, and then I'm also looking for students working on decompression for GPUs with combination of database systems. Yeah, and here you see an example for the data blocks. When they are compressed, here we have the dictionary, we have the compressed data, and we have some offsets for fast execution. And as I said, we have SIMD processing, so we can access the same data in parallel. So actually I have one slide on. Yeah. Let's do it next week. Code generation. Okay, so let's make a break. Let's make a break of 15 minutes. When should we meet again? So 15 minutes would be... Let's meet again when this clock shows 6 o'clock. So in how many minutes of delay? 5 minutes. So it would be 5 to 6. So at 6, so at 5:55 we meet again. So